Alright, hello physics students, welcome to term 2 but also your online learning. We are commencing unit 4, which is electromagnetism and quantum theory, and we're going to start with the first topic, which is electromagnetism or electrostatics. You can open up your books to a brand new page and your title should be Electrostatics. Okay, before we start, just a little bit of background information. Some of this will be a repeat from our previous topic, electrical circuits. The static charge is, generally speaking, static electricity built up on the surface of an insulator, such as a plastic comb. And you guys have all experienced this jumping on the trampoline or rubbing a balloon across your hair, something like that. The charge that has built up cannot easily flow away from the insulator, which is why it is called static electricity. You have all experienced this before. Well, where does this static electricity come from? As you remember from year 10, an atom contains electrons, and from the previous topic, electrons is the flow of electricity. An atom has an equal amount of negative and positive charges which balance each other out. And electrons do not stay attached to the atoms and they can sometimes be removed by rubbing, and this is where we get static electricity. Build-up of static charge. Generally speaking, when we rub two items together that are insulators, one material will end up with more electrons, which overall has a more negative charge, remembering that electrons have a negative charge generally. And then also one of the materials will have fewer electrons and then it will have a positive charge. Just an example that shows how friction can be used to create a static charge. If an insulator, which is our plastic rod here, is rubbed with a cloth, it can be charged in one of two ways. In the first example, electrons move from the cloth to the insulator, and you can see here that the cloth has less negative charges, and as a result the insulator ends up with an overall negative charge because it now has more electrons than protons. In the second example, electrons move from the insulator to the cloth, and you can see here that the insulator is losing electrons and the cloth gains electrons. The insulator would end up with an overall net positive charge, and you could imagine that the cloth itself would end up with a net overall negative charge. Forces between charges. Let's take a little look here at two acetate rods, and you can see looking at the diagram that both of them contain positive charges. And what you'll also see is that the rods are repelling each other. Now the reason that they're repelling each other is because opposites attract, and if the charge is similar, then they will repel. Some notes that I would like you to take down in your books. New subheading, forces between charges, and the rods repel each other because they have the same overall charge. And just take down this quick diagram here. Pause the video if you need to. Another quick example for you for forces between charges. In this case here, we've got a polyethylene rod and an acetate rod, and the polyethylene rod has a net positive charge, whereas the acetate rod has a net negative charge. And you can see that the rods are attracted to each other. Now the reason that they're attracted to each other is because they have an overall opposite charge and hence attract one another. Just a quick example for you for static electricity, and you can see from the picture that the static electricity from the plastic slide causes the child's hair to stand on end. The sliding motion stripped electrons away from the child's body, leaving an excess positive charges which repel along each other and each strand of hair. Very cool stuff. Okay, this is where we officially start the course content, and this is 4.1.1.1, which is to define Coulomb's law. Let's go ahead and do that now. Okay, forces on electrostatically charged objects. The magnitude or the size of an electrostatic force F between point charges Q1 and Q2 separated by a distance r is given by Coulomb's law, and we'll define that on the next slide. What you can see here in my diagrams is that I've got a point charge Q1, a point charge Q2 separated by my distance r, and there is a force between those two like charges. Now, important to remember that because they're like charges, they are repelling one another, and if they are unlike charges, as in my second diagram, they are now point charges Q1 and Q2 separated by a fixed distance r, and these are attracting one another. You can go ahead and write down everything that I have highlighted, and if you need to, pause the video now. Okay, I've just got a couple of multiple choice questions for you. What does the letter K refer to in the following formula? F equals K multiplied by Q1 times Q2 divided by R squared. Is it A, the speed of light, B, the electrostatic force, C, the size of the charge, or D, Coulomb's constant? I'll let you pause the video now and have a go. Otherwise, the answer is it's a Coulomb's constant. Now, really important, in your data booklet, it may be given as 1 divided by the quantity 4 pi times this little e thing that you might not have seen before. Now, this thing here is the permissivity of free space constants. However, all you need to know is that the entire quantity is equal to 9 times 10 to the 9, and that's what's given in your data book. I just wanted to make you aware of that. You may see it written like this. A couple more multiple choice questions for us. What does the letter R refer to in the following formula? Is it either A, the speed of light in a vacuum, B, electrostatic field, C, Coulomb's constant, D, distance between charge? I'm going to let you pause and have a go. Okay, it is the distance between charges. R is, of course, our distance between the charges. Really important that we're always in meters. Next multiple choice question. If a positively charged proton enters the electric field of a negatively charged electron, what would happen? Either A, the proton feels an attractive force that pulls it toward the electron, B, the proton feels a repulsive force that pushes it away from the electron, C, the proton absorbs the electron and is converted into a neutron, or D, both particles become frozen in position for the rest of eternity. I'll let you pause the video now and have a go. Okay, if a positively charged proton enters the electric field of a negatively charged electron, the proton feels a repulsive force that pushes it away from the electron. That is, of course, because we have a positively charged proton, a negatively charged electron, and we remember that protons and electrons generally repel one another because their charges are unlike. Okay, two more multiple choice questions for you. The first one, what will be the force if the distance between them is halved? I want you to pause the video now and have a quick think about it, maybe do some calculations, and I will discuss the answer in a moment. Okay, to solve this guy here, we need to actually think about the equation. F equals K times Q1 times Q2, whole thing divided by R squared. Now, if the distance between them is halved, all of a sudden R becomes R on 2. So let's put that into our equation. And what will happen when we square this is the numerator will stay the same. However, now all of a sudden we have R squared on 2 squared. Now rearranging this means that 2 squared is 4, and our force will increase by a factor of 4. Which of the following is false? I'm going to give you a brief moment to read those, pause the video if you need to, and then come up with an answer. You should have got none of the above. If you do the mathematics, you should be able to figure out that all of those are true. Okay, this is now dot point 4.1.1.2, which is to solve problems involving Coulomb's law. Let's go ahead and do it. Okay, we're going to do some problems. I'm going to do a few, you're going to do a few, and then I'm going to do the answers for you. 2 protons are placed next to each other 2.4 times 10 to the negative 9 meters apart. They each have a charge of 1.6 times 10 to the negative 19 coulombs, and they repel each other. What is the size of the repulsive force that one proton exerts on the other? Be sure to include SI units. Okay, to solve this problem, we need to use our formula. F equals Q1 times Q2, whole thing multiplied by our constant K divided by R squared, the distance between them. Now I can see here that my charges for both of those guys are the same, and then the distance between them is R squared. Now you need to remember your constant K is 9 times 10 to the 9. Substituting in those values, we get 9 times 10 to the 9, we get our distance between them, and then we also get our charges. Both of them are the same. Putting that into a calculator, you should get force equals 4 times 10 to the negative 11. Now the question says, be sure to include SI units, and that's what I've done. Force is measured in newtons. Okay, question number 2. 2 negative charges are placed next to each other 0.29 meters apart. Just highlighting some key information here. They each have a charge of negative 5 times 10 to the negative 6 and repel each other. What is the size of the repulsive force that one charge exerts on the other? What I'm really interested in finding out is the size of the repulsive force. And I'm going to use my formula. F equals K times Q1 times Q2, whole thing divided by R squared. I want you to have a go at this problem here. Keep in mind that K is 9 times 10 to the 9. Off you go. I'm going to do this one in a moment. You can pause the video now. Substitute in those values. Got my first substitution, which is 9 times 10 to the 9, which is my K. And then I've got my charge of my particles, and then I've also got my radius. Put that into a calculator, you should get force equals 2.7 newtons. Now really important there that I've kept my units as the question specifies. Okay, question number 3, another force calculation problem. A proton and an electron are positioned 5.4 times 10 to the negative 12 meters apart. The proton has a charge of 1.6 times 10 to the 19 coulombs, and the electron a charge of 1.6 times 10 to the negative 19 coulombs. What is the size of the attractive force between them? Be sure to include SI units. I want you to pause the video now, have a go at this problem, and we'll do it in a moment. Okay, I've got my formula. F equals K times Q1 times Q2, whole thing divided by R squared. Substituting in those values, we know our constant is 9 times 10 to the 9. We also know that the charge of our proton is 1.6 times 10 to the 19, and we also know the charge of our electron. The distance between them is given here, 5.4 times 10 to the negative 12. If you put that into a calculator, you should get force equals 2.7 newtons. Okay, I want you to have a go at this problem, but before you do that, I'm going to give you a couple of tips. What is a repulsive force between two pith balls that are 8 centimeters apart and have equal charges of negative 30 nanocoulombs? And the question wants you to use K 8.99 times 10 to the 9. Now, your data book does use K as 9 times 10 to the 9, and in your external exam, you should use that value, but for this problem, we're going to use K as 8.99 times 10 to the 9. Now, if you remember back, the formula requires the distance between our charges to be in meters, so you'll need to do a unit conversion here. And you can also see here that our charges has some scientific notation in here. This is a nanocharge, so you have to factor that into your equation. I want you to use the formula here, substitute the values. Pause the video, have a go, and we will do the problem in a moment. Okay, substituting in our known values, we know that K is 8.99. I've done a unit conversion here. 8 centimeters is indeed 0.08 meters. And then it's equal charges, so I've just decided to square the charge. This is negative 30 times 10 to the negative 9. The negative 9 comes from my nano. And if you put that into a calculator, you should get F equals 1.27 times 10 to the negative 3. I think when I put it into my calculator, I actually get F equals 0.00126. That's okay, I've just done a little bit of rounding and put in some scientific notation here. Okay, this is a problem that I might do and walk you through. However, if you would like to have a go at this problem, then I encourage you to pause the video now and have a go yourself. Otherwise, I'm going to do this one. How strong is the attractive force between a glass rod with a charge of 0.7 microcoulombs and a silk cloth with a charge of negative 6 microcoulombs, which are 12 centimeters apart, using the approximation that they act like point-like charges? Now, the formula that we have here assumes that the charge is a point-like charge. Now, what that means is that if we have a particle, the charge is directly in the center, and that particle is small enough to act like a point. Now, this problem here involves real-life things, such as a glass rod and also a silk cloth. These aren't point-like charges. However, we can assume and approximate the force between them, assuming that they act like point-like charges. There's a second half to this problem. It says, discuss how the answers to this problem might be affected if the charges are distributed over some area and do not act like point-like charges. First things first, let's just calculate the force, substituting in our values that we know. We know our K value is 9 times 10 to the 9. We know that the glass rod has a charge of 0.7. Now it's times 10 to the negative 6 because it is indeed a microcoulomb. And then the cloth has a charge of negative 6 microcoulombs, and that's where my 10 times negative 6 comes in. And then I've also had to do a little bit of a unit conversion here because my distance between them is 12 centimeters. Just converting that to meters is 0.12. Popping that into a calculator, you should get negative 0.2622 newtons or 0.262 newtons, just doing a little bit of rounding there. Now that second question there, discuss how the answer to this problem might be affected if the charges are distributed over some area and do not act like point charges. Assuming that the center of mass is separated by 12 centimeters, the answer in part A is only true if the charges are connected or concentrated at their center of mass. If, however, the charges are distributed over an area, as you would probably expect in a rod or some silk, then the concentration of the charge along the side closest to the oppositely charged object will increase the net force. Okay, I'm going to walk you through a couple of harder problems here. This problem says 2-point charges exert a 5 Newton force. In this case here, we're given the force exerted on the point charges. And the question says, what will the force become if the distance between them is increased by a factor of 3? Now we know from the formula that force is inversely proportional to the separation distance squared. And let's say that the force exerted on the first particle is given by the formula K equals Q1 Q2 divided by R squared, and then also the force exerted on the second particle is F2, which is equal to K times Q1 Q2 divided by R squared. Now what we can do is find the ratio of forces, and this will help us solve this problem. So I'm going to do F2 divided by F1 here. And because force is inversely proportional to separation distance, we come up with this. R1 squared divided by R2 squared. I'm just going to put the squared outside of the fraction and put brackets around him. And I come up with this really neat formula, which is F2 is equal to the F1 multiplied by R1 divided by R2 whole thing squared. What this allows me to do is make some really nice substitutions, because I know that the point charge exerts a 5 Newton force, and I know that R1 and R2 are 3 meters away from one another. I put it into my fraction here, and I get force number 2 will be 0.556 newtons. A little bit of a tricky one there, but nothing that you aren't capable of. Okay, another problem for you. How far apart must 2 point charges of 75 nanocoulombs, and this is typical of static electricity, be to have a force of 1 Newton? Okay, first thing that we need to do is recall our formula, and then we're going to rearrange that for R, and you should get a formula like this. I want you to have a go at using the highlighted formula, substituting in the known values, and finding the distance between them. Pause the video now and have a go. Okay, substituting in those values, you should have got K as 9 times 10 to the 9, as it always is. Both of these charges have a charge of 75 times 10 to the negative 9, that is nanocoulombs. Whole thing squared divided by a force of 1 Newton. Then I've got to the power of half for my square root. Putting this into a calculator, you should have got 0.007 meters. Okay, a question for you to do. If 2 equal charges, each of 1 coulomb, are separated in air by a distance of 1 kilometer, what is the magnitude of the force acting between them? Now, what you should see in this problem is that even at such a large distance of 1 kilometer, the repulsive force is quite substantial, and that's because 1 coulomb is quite a significant amount of charge. When you do this problem, you'll have to make sure that you are converting your 1 kilometer units into meters. Use the formula, have a go. I'm going to do the problem for you in a minute. Pause the video now. Okay, substituting in those values, K is 9 times 10 to the 9, as it always is. Equal charge of 1 coulomb, so I've just put 1 squared there. Whole thing divided by 1 times 10 to the 3. The reason I've got a 10 to the 3 there is because it is kilometers. Whole thing squared as the formula states, and then the force I get is 9 times 10 to the 3 newtons. Never forgetting my units there. Okay, I've got a slightly tricky question for you. One that you might see in an external exam situation. A test charge of 2 microcoulombs is placed halfway between a charge of 6 microcoulombs and another of 4 microcoulombs separated by 10 centimeters. What is the magnitude of the force on the test charge? One thing I want you to do is try to draw a diagram of what you see here in this problem. Pause the video now, draw that diagram, and then I'm going to show you what I came up with. Okay, the diagram I have here is I've got my test charge here, okay, and that is 2 microcoulombs. Now the question says that it's halfway between another charge, which is 6 microcoulombs, and then another charge, which is 4 microcoulombs, and the total distance between them was 10 centimeters. Now, if it's midway between these two, it must mean that there is 5 centimeters on either side. The question asks, what is the magnitude of the force on the test charge? So what we might do is find the force exerted on the test charge by Q2, find the force exerted on the test charge by Q1, and then we'll subtract them and see what happens. First things first, let's find the force on the test charge and the Q1 that I've called here. Substituting in known values, we get 9 times 10 to the 9 times 4 times 10 to the negative 6 times 2 times 10 to the negative 6, whole thing divided by 0.05. Keep in mind I've converted to meters here. I get my answer 28.8 newtons. I'm going to do the exact same process now for the force between the test charge and the charge with 6 microcoulombs, and I get 9 times 10 to the 9, 6 times 10 to the negative 6, 2 times 10 to the negative 6, divided by my radius, same thing again, 0.05. And I also get 43.2 newtons. What this means is that Q2 is pushing with a force of 43.2 newtons, and Q1 is pushing with a force of 28.8 newtons. Now, if we subtract them or find the difference, we will find the overall net charge exerted on my test charge, and that works out to be 14.4 newtons. Okay, another problem that you might see on an external exam situation. The question I've got here is calculate the acceleration of 2 isolated protons separated by 2 nanometers, which is a typical distance between gas atoms. And it's got here in the question, the charge of a proton is 1.6 times 10 to the negative 19 coulombs. Now, I've actually included the charge of a proton, however, it might not necessarily always be given to you in the question. The reason being is because you can actually find this information in your data book. So if the charge of a particular proton or neutron isn't given to you in the question and you don't know it, you're not expected to recall that information. You should look to your data book to find that information. I've included it for the sake of this question, however, future questions might not have it. We're being asked to calculate acceleration. Now you might say to me that, hang on, what does acceleration have anything to do with electrostatics? Well, we know that force is equal to K times Q1 times Q2, whole thing divided by R squared. But we also know from year 10 science that force is equal to our mass times our acceleration. Now, if we combine those two formulas, we should get something that looks like this, where acceleration is equal to K multiplied by the charge. Now, because we're dealing with two protons and they both have the same charge, I'm just going to call that Q squared, whole thing divided by mass of a proton, and then the radius between them, which is 2 nanometers. As I stated before, the mass of a proton isn't actually given to us here. You'll have to find it in your data book. I've got here, substituting in the values, 9 times 10 to the 9 for K, 1.6 times 10 to the negative 19 for the charge of my proton, the mass of my proton given in my data book, 1.67 times 10 to the negative 27, and then the distance between them found in the question, 2 times 10 to the negative 19. Now my answer, 3.45 times 10 to the 6 meters per second squared. Really, really important that my units for acceleration are meters per second squared. Bit of a trickier problem for you, one that you might see here in your external exam, that requires you to draw information from multiple sources, as well as utilizing your data book, finding information for the mass and the charge of a proton. Okay, this is now 4.1.1.3, which is electric fields and electric field strength. Okay, electric fields. If the amount of force acting on a charge is known, it is possible to say something about how strong the electric field is. Electric field strength, usually given by E, or field density, is given by the amount of force acting on a particle divided by its charge Q. Now, in a proton or a neutron, the electric field around a proton isn't the same in all directions, and that's because the fields are radial. Something to keep in mind. However, in a uniform field, where all the lines are parallel or evenly spaced out, as in this diagram here, the electric field strength, that is E, is the same at every point in the field, and you get what's called a uniform electric field. We can do this by having two conducting plates, one with a positive side and one with a negative side. I would like you to take the notes that are highlighted on the screen, pause the video if you need to. Okay, we're going to go ahead and solve some problems involving electric fields. Before we do that, I want to give you the formula for it. The magnitude of the strength of the field is given by this formula here. I've got E is equal to the force of the field divided by the charge. Now, sometimes you might see the formula written like this. Remember that 1 divided by 4 pi times this weird E thing is actually the permissivity constant, which is 9 times 10 to the 9, or K. My Q is my charge, and then my R is my distance between the two objects. I would like you to write down that formula there. Off you go. Okay, a couple of multiple choice questions for you. What word do physicists use to describe the shape of the electric field around a point charge? Now, a neutron is an example of a point charge, and this diagram might be able to help you. Is it either uniform, regular, spiky, or radial? Well, you have got that problem now. Pause the video if you need to. Okay, it is indeed radial. As you can see in the diagram, all of the electric fields point inwards, and that is because it is a neutron with a negative charge. Does a radial electric field have a constant field strength? Have a go. Okay, the answer is no. That is, as you get closer to the point charge, the strength of the electric field becomes greater. That is greater as we get closer. It becomes weaker as we get further away. Okay, multiple choice question number 3. What word do physicists use to describe the shape of an electric field in which the field lines are parallel and evenly spaced, as in this diagram here? Is it A, uniform, B, square, C, purple, or D, radial? Okay, the answer is indeed uniform. As you can see, the field strength is uniformly distributed between the two positive and negative charges. Does a uniform electric field have a constant strength? And the answer is yes. 2 more multiple choice questions for you. Several electrons are inserted into a uniform electric field at the positions shown below. Which electron will experience the smallest force? So my electric field is given in the diagram. My electrons are here, A, B, C, D. Which one experiences the smallest force? Okay, they should all experience the same force, and the reason being is because they're in a uniform electric field which has a same strength throughout. That is, it is uniform. What is the correct SI unit for electric field strength? Now it's newtons per coulomb. Gave away the answer there. Okay, time to do some problems. An alpha particle, which is a radioactive decay product made of 2 protons and 2 neutrons, has a net charge of 3.2 times 10 to the negative 19 coulombs. Let's say it's introduced into a uniform electric field and experiences a force of 7 times 10 to the negative 12. Calculate the field strength of the electric field. Very, very straightforward. Take our formula. Field strength equals force divided by charge. Substitute in our known values. We've got 7 times 10. And then we've got 3.2 times 10 to the negative 19. Putting into a calculator, you should get 2.2 times 10 to the 7. Really, really important that we are not forgetting our units. And you might see here I've written NC to the power of negative 1. Now NC to the negative 1 is just another way of writing N divided by C. That is newtons per coulomb. Okay, a problem that I would like you to have a go at, very similar to the previous one, substitute in the values. A positron, which is called the antimatter equivalent of an electron, has a charge of 1.6 times 10 to the negative 19 coulombs. Suppose it introduced into a uniform electric field where it experiences a force of 6 times 10 to the negative 15. What is the strength of the electric field? Use the formula and substitute in the known values. Pause the video now, have a go. Go through the answer in a second. Okay, substituting in our known values, our force, 6 times 10 to the negative 15. And then we've got our charge, 1.6 times 10 to the negative 19. Putting that into a calculator, you should get 3.8 times 10 to the negative, 10 to the positive 4 rather, newtons per coulomb. Making sure we're not forgetting our units. Okay, another question. What is the magnitude and direction of an electric field that exerts a 2 times 10 to the 5 Newton upward force on a negative 1.75 microcoulomb charge? Similar thing again, we're going to have to use our formula. E equals F on Q. However, you need to have a little bit of a notation in this problem. Up is positive and downwards is negative. If your answer you get is positive, that means the direction of the electric field will be upwards. And if you get a negative answer, the direction of your electric field will be downwards. Substituting in our new known values, F is 2 times 10 to the 5 and Q is 1.75 times 10 to the negative 6. Putting that into a calculator, you should get 11.4 newtons per coulomb. Now I've got downward here because my answer is negative, which means that the direction of my electric field is downwards. Okay, a little bit more of a trickier question for us. Suppose a proton and an electron are positioned 6.2 times 10 to the negative 12 meters apart. The proton has a charge of 1.6 times 10 to the negative 19 coulombs, and the electron a charge of negative 1.6 times 10 to the negative 19 coulombs. What is the strength of the electric field at the location of the proton? Be sure to include SI units. Now to begin this, we know our formula E equals F on Q. However, we aren't actually given a force F. So we're going to have to go ahead and calculate this. Now how we're going to calculate this is by using our formula from before, our force on electrostatically charged objects. Formula is F equals K times Q1 times Q2 divided by R squared. Now in this equation, my values that I need are my constant K, my charges Q. Both of them have the same charge. One's just positive and the other is negative. And then I've got my distance between them. Distance between them is 6.2 times 10 to the negative 12 meters apart. My force I work out to be is 5.994 times 10 to the negative 6. Now, I've got to find the magnitude of my field strength using the formula E equals F on Q. The F in this equation is just my F from before, so I can substitute him in. Now it's asking for the strength of the electric field at the location of the proton. So when I substituted my charge Q, I'm going to substitute in the charge from the proton. That is 1.6 times 10 to the negative 19. And my force just comes from here. 5.994 times 10 to the negative 6. Substituting into a calculator, you should get 3.7 times 10 to the 13 nanocoulombs. Okay, another problem. What is the magnitude and direction of the force exerted on a 3.5 microcoulomb charge by a 250 Newton per coulomb electric field that points due east? We have our formula E equals F on Q, and if we rearrange that, we should get F equals QE. Substituting in our known values, Q is 3.5 times 10 to the negative 6, and E is 250. Substituting in these values, you should get 8.75 times 10 to the negative 4 newtons. Another problem for us, some field strength calculations. Calculate the magnitude of the electric field 2 meters from a point charge of 5 microcoulombs. This type of charge is what you would find on the terminal of a Van de Graaff. First thing I need is I'm going to actually have to combine my formula. I gave this one to you earlier, but it's combining the formula from the field strength as well as the electric field formula. In this equation here, K is 9.9 times 10 to the 9, and my charge is 5 times 10 to the negative 3. Whole thing divided by my distance, 2. You should get 1.12 times 10 to the 7 newtons per coulomb. Okay, another problem for us. What magnitude point charge creates a 10,000 Newton per Coulomb electric field at a distance of 250 meters? And there's a second part to this problem which asks, how large is the field at 10 meters? First thing we need to do is we're given our formula E equals KQ divided by R squared. And because we're asked for the magnitude of the point charge, we're going to have to rearrange that for Q. The formula is now Q equals R squared E divided by K. In this question here, my distance is 250 and my magnitude is 10,000 divided by K. K is 9 times 10 to the 9 as always, and the answer you should get here is 6.95 times 10 to the negative 18. The second part of that problem says how large is the field at 10 meters? So we're going to do the exact same thing again, and we're going to use the original formula this time, E equals KQ divided by R squared. As always, K is 9 times 10 to the 9. My Q comes from the previous question, and then the distance between them is 10, as said in the problem. Putting that into a calculator, you should get 6.24 times 10. Okay, another tricky question, but similar to the one we did earlier. It says calculate the initial from rest acceleration of a proton in a 5 times 10 to the 6 electric field. And the information it gives us is that the charge of a proton is 1.6 times 10 to the negative 19 coulombs. Now, this problem here seems like that might not be enough information to be able to perform the calculation, and that's because you'll need to find some information in your data book. We know that the force is equal to mass times acceleration, but force is also equal to QE. We did that rearranging before. Combining these two equations, you should get acceleration equals QE divided by m, where Q is our charge, E is our electric field strength, and m is the mass of our proton. Now you'll see that the mass isn't actually given anywhere in the question, and that's because you'll have to refer to your data book. However, we can substitute in our known values. We get our charge 1.6 times 10 to the 19, and that's given in our question, multiplied by E, the electric field strength, and that is 5 times 10 to the 6, divided by the mass of our proton. You can find that information from your data book. Putting this into a calculator, you should get 4.79 times 10 to the 14 meters per second there. Really important that you are putting in the correct units. Okay, this is now dot point 4.1.1.5, which is to define and solve problems involving electrical potential energy. Let's do it. Okay, electrical potential energy, a little bit of reading for us to do. One of the most important ideas in physics is the concept of energy. It comes in many different forms: kinetic, chemical, gravitational, elastic, and many others. As you might expect, there is energy associated with an electrostatic field. This energy is called electrical potential energy because it is stored in the charged particles that inhabit that field. Having potential energy means there is the potential for a charge to move within the field. We have seen that point charges can attract or repel each other according to Coulomb's law. When they do so, they accelerate and gain kinetic energy. The kinetic energy gained is equal to the potential energy that the particle loses. The diagram shows the field created between two oppositely charged rods, one positive and one negative. There are two charged particles in the field, and are they where you would expect them? The positive charge is next to the positive rod, and the negative charge is next to the negative rod. This is a very high energy state, because as we've always been told, like charges should repel and move away from each other. The particles have a very high electrical potential energy. After some time, the particles have moved. Their potential energy is converted to kinetic energy as they accelerate across the electric field. The positive charge ends up stuck to the negative rod, since opposites attract, and the negative charge sticks to the positive rod. This is a low energy state, because the particles now have the minimum potential energy. In our equations, U is used for the symbol for electrical potential energy, and change in U, or delta U, is for a change in potential energy. This is to avoid getting it mixed up with E, the electric field strength. A couple of multiple choice questions for us. What is the best definition for electrical potential energy? A, the energy stored in a charged particles in an electric field. B, the energy carried by the brainwaves of a bright spark like you. C, the energy released when lightning strikes the ground. Or D, the energy an electron has due to movement. I want you to pause the video now and have a go. Okay, the answer is indeed A, the energy stored in a charged particle in an electric field. Question 2, what is the best definition for the kinetic energy? The energy of a moving object due to its movement. B, the energy of a stationary object due to the temperature. C, the magnitude of force acting on a moving object. Or D, the magnitude of the force acting on a stationary object. Pause the video now, have a go. Okay, the answer is indeed the energy of an object moving due to its movement. Multiple choice question number 3. What is the SI unit for energy? Haven't explicitly told you this, but you should be able to recall that it is indeed joules. What does the law of conservation of energy tell us? And you should also be able to recall this from previous years of science. A, energy cannot be created nor destroyed, only converted from one form to another. And hopefully you don't need to go through any of the other answers, because that is indeed the answer. Multiple choice question number 5. Identify the best definition for a uniform electrostatic field. A large grass area in a school where games and sporting events take place. B, a field where the position of a charged particle influences the forces felt by it. C, a field where the position of a charged particle doesn't influence the force felt by it. Or D, the arrangement of the charged particles in a magnetic field. Okay, the answer is indeed C, and the reason it doesn't influence is because it's a uniform electrostatic field, and that means that the position doesn't influence the force, and the force is the same throughout. Multiple choice question number 6. A capacitor is a device that uses the energy stored in an electric field between two conducting plates. What type of energy would be stored? The answer is electrical potential energy. Okay, work on a charged particle. When a particle is moved through space by an electric field, it is said that the field does work on the particle. We can calculate the work done by any object. It's W, and it's given by the force multiplied by the distance S. Now what you should be able to recall is that E multiplied by Q is actually our force. And then we have our S, which is the distance. And that is that the distance that the particle has moved, usually measured in meters. Right, let's go ahead and use that formula to perform some calculations. An electron finds itself in a uniform electric field and accelerates from rest towards the more positive side of the field. The field strength of the field is 56,000 newtons per coulomb. After traveling 1.5 meters in a straight line, calculate how much kinetic energy the electron has gained. Now this formula doesn't actually have kinetic energy in it. However, the work done is equal to the kinetic energy. Now you'll also notice when we substitute in our known values, the field strength is 56,000, and then the charge of the electron 1.602 times 10 to the negative 19 isn't actually given in the question. That's because you have to refer to your data book for this value. If you're given this question in an external exam, have to look at your data book to find that value. Then the distance between them is indeed 1.5 as given in the problem. Putting this into a calculator, you should get work equals 1.3 times 10 to the negative 14 joules, and this is the kinetic energy. Okay, a problem for you to do. I'd like you to pause the video now, read the question, using the formula, substitute the known values into the equation, and solve for the answer. Off you go. Okay, a large positively charged particle is exposed to the uniform electric field. It is initially at rest and accelerates along the lines of the field. The strength of this field is 14,000 newtons per coulomb, and the particle carries a charge of 2.4 times 10 to the negative 15 coulombs. After traveling 1.25 meters in a straight line, calculate how much kinetic energy the particle has gained. Similar thing again, using our formula, W equals EQS. In this case here, our strength of our electric field is 14,000, and the charge is given to us in the problem, as well as the distance between them. Not a problem that's too difficult. Okay, that concludes everything that you need to know about electrostatics. I hope you've enjoyed our first online lesson, and there'll be a few more to come. Thank you, bye.